One of the primary assumptions for those who put their trust in science is that matter is all that matters. Only that which can be experienced through the senses, that which can be seen or heard, smelled, tasted, or touched, can give man any real knowledge or truth. The idea of materialism, that matter or that which is physical is the only thing that exists, isn't a new idea. For example, the Greek philosopher Democritus, who lived from 460 BC to 370 BC, founder of atomism, said this: "The first principles of the universe are atoms and empty space. Everything else is merely thought to exist." And an often quoted variant of this saying is that nothing exists except atoms and empty space. Everything else is opinion. It should come as no surprise that many consider Democritus to be the father of modern science. But as popular as this idea continues to be, that matter is all that matters, is there perhaps more to this matter than meets the eye? If we accept the proposition that matter is all that matters is true, then what can science tell us about matter? What kind of knowledge or truth can studying matter give us? Let's define our terms so that we can fully appreciate the matter. Now, defining matter can be difficult, but at the most basic level, the universe is made up of two types of matter: baryonic matter, which includes atomic matter, and non-baryonic matter, which includes dark matter. Baryonic matter, sometimes called ordinary matter, can be defined as material substance that occupies space, has mass, and is composed predominantly of atoms. Nearly all of the matter that is encountered or experienced in everyday life is made up of atoms, or is ordinary atomic matter. So then, what does science tell us about ordinary atomic matter? Science estimates that only 4 to 5% of the entire universe is actually made up of atoms, or visible matter. Every atom of visible matter is divided into two parts: the nucleus, which contains protons and neutrons, and the electron cloud. But what about the distance between the electron cloud and the nucleus? This distance is huge. For example, if a nucleus were the size of a golf ball, it's been estimated that the electron cloud would be located about 1.5 miles away. What is the empty space between the nucleus and the electron cloud of an atom filled with? Science can't tell us because it's not observable. Over 99% of an atom is empty immaterial space, which means only less than 1% of an atom is actually observable matter. Think of how much empty immaterial space that is, and all of it's unaccounted for. What is it? No matter. All right. If over 99% of an atom is unobservable empty space, this leaves only the electron cloud and the nucleus of an atom for us to actually observe. So let's move on to the moving electron. Electrons travel in specific orbits and move at incredibly high velocities around the nucleus of an atom. However, it's impossible to ever know with certainty both where an electron is and where it's going next. This is referred to as the Heisenberg uncertainty principle. To know the velocity of an electron, we must measure it. But to measure it, we're forced to affect it. Therefore, we cannot know with certainty both where an electron is and where it's going next, because the moment we try to observe an electron, we change the electron's velocity. It's called the Heisenberg uncertainty principle for a reason. For how can we have certain knowledge about something that changes the moment we observe it? Thus far, it doesn't seem like we know an atom from atom. Since true knowledge about the electron is so elusive, let's turn to the nucleus of an atom to see if we can get this matter cleared up. The nucleus of an atom is made up of protons that are positively charged, along with neutrons that have no net electrical charge. If opposite charges attract and like charges repel, what keeps the protons within the nucleus from flying apart? In other words, what explains the nuclear force that holds every nucleus of every atom together? Well, the scientist's answer is to put a quark in it. Quarks are meant to explain the nuclear force that keeps protons and neutrons together. It gets quirkier. There are 6 types of quarks, known as flavors. There's an up quark, down quark, strange quark, a charm quark, a bottom quark, and a top quark. It should be noted, however, that no one has ever seen a quark by itself. Quarks have never been directly observed or found in isolation. So let's review. What are we actually looking at here? Science can't account for the empty immaterial space between the nucleus and the electron cloud of an atom, which, by the way, makes up over 99% of an atom. And of the remaining less than 1% of an atom that can be measured, science can't tell us with certainty the exact position and velocity of an electron at any given point in time. And science's answer to what keeps the nucleus of an atom from exploding, the nuclear force, is quarks, even though no one's ever actually seen or isolated a quark. Now, to make matter worse, here is a different matter altogether: dark matter. Science estimates that roughly 23 to 25% of the universe consists of non-baryonic, cold, dark matter. This cold, dark matter is a hypothetical form of matter that is invisible. It doesn't absorb or emit light, and it doesn't collide with atomic particles, but exerts gravitational force. To repeat, dark matter is hypothetical. It's not made of atoms. Like the empty space between the nucleus and electron cloud of every single atom, dark matter is unobservable. So if only 4 or 5% of the universe is made up of visible baryonic matter, atoms, and another 23 to 25% of the universe is made up of non-baryonic matter, which is this hypothetical dark matter, what makes up the rest, over 70% of the universe? Answer: dark energy. The universe is expanding at an accelerating rate, and scientists attribute this accelerating expansion to dark energy. So called because its exact nature remains a mystery, but something must fill the vast reaches of space to account for the accelerating expansion. Dark energy is the name given to the anti-gravitating influence that's accelerating the rate of expansion of the universe. It's not composed of known particles like protons, neutrons, or electrons, nor of the particles of dark matter, because these all gravitate. With so much scientific speculation and uncertainty about atomic matter and dark matter, how trustworthy is the proposition that matter is all that matters? That truth can only come from knowledge of matter, especially since observable matter is only the tip of the iceberg of our universe. 70% or more of the universe doesn't even consist of any matter at all. It would appear that our knowledge of matter leaves much to be desired. What should we place our faith in? The false lines of science or the true lines of Scripture? What holds atomic matter together? The power of Christ or the power of quarks? Which is a sure foundation for explaining the universe? Dark matter, dark energy, or the light of the world, Jesus Christ? Let's step out of the darkness and into the light. Colossians 1:15 through 17 says, "He," that is Jesus Christ, "is the image of the invisible God, the firstborn over all creation. For by him all things were created that are in heaven and that are on earth, visible, or material, and invisible, immaterial, whether thrones or dominions or principalities or powers. All things were created through him and for him. And he is before all things, and in him all things consist." Again and again we see, pun intended, that our eyes, our power of observation, deceive us and cannot give us objective truth. Only God can reveal objective truth to man. Now, in the next part of the class, we will look at one final example of how our powers of observation can deceive us by asking, how old is the Earth and how old is the universe? Stick around, you won't want to miss this one.